In the previous video, we learned Dijkstra's algorithm. It expands the node with the smallest known cost so far. That is enough to prove shortest paths when edge weights are non-negative. But sometimes we do not want to search outward in every direction. We want the search to move toward one specific goal. That is where E star begins. It keeps Dijkstra's exact cost from the start, then adds one more signal, an estimate of the remaining cost to the goal. With that extra estimate, the search becomes goal-directed instead of purely cost-driven. To make this concrete, we will work on a grid. Each walkable cell is a node. A move to a neighboring cell is an edge. Walls are blocked cells, so they have no outgoing moves. If every move costs 1, then the exact cost of a path is just the number of steps. The start cell is the source. The goal cell is the destination. So even though the visuals look like a map, the algorithm is still running on a graph. The grid just makes the graph easier to see. The new ingredient is the heuristic. For any cell n, the heuristic h of n estimates the remaining cost from that cell to the goal. It is not the true future cost. It is a guess that helps rank candidates. Dijkstra only asks, how much has this path cost so far? This search asks two questions. How much has this path cost so far? And how far does this cell still seem from the goal? That second question gives the search direction. A star ranks a cell with f of n equals g of n plus h of n. G of n is the exact cost from the start to n. H of n is the estimated cost from n to the goal. F of n is the total priority. So a cell can be attractive in two different ways. It can be cheap to reach already, or it can look close to the goal. The algorithm balances both signals. The open set always chooses the cell with the smallest f value. On a 4-direction grid, the standard heuristic is Manhattan distance. That means horizontal distance plus vertical distance to the goal. It matches the movement rules, because every move changes one coordinate by one step. If diagonal movement were allowed, a different heuristic would fit better. The rule is simple. The heuristic should reflect the geometry of the moves you actually allow. A good heuristic gives direction without inventing impossible shortcuts. Now let us run EA star. We start at S. Its G value is 0 because the cost from the start to itself is 0. Its H value comes from the heuristic, so its F value is just H at the beginning. We place S into the open set and pop it first. Then we inspect its neighbors. Each neighbor gets a tentative G, a heuristic H, and therefore an F value. Those neighbors enter the open set. The next current cell is the one with the smallest F, not necessarily the one with the smallest G alone. As search meets walls, the frontier bends around them. Some cells stay promising because their H value is low, but a wall can still make their real route expensive. When we find a better route into a cell, we update its G value, recompute F, and change its parent pointer. If a new route is worse, we ignore it. This is the same relaxation idea from Dijkstra, but now the open set is ordered by G plus H instead of only G. Eventually, the goal cell rises to the top of the open set. At that point, under the right heuristic conditions, the optimal path has been found. The algorithm does not need to finish the entire grid. It can stop when the goal is selected. Then we reconstruct the path by following parent pointers backward from the goal to the start. Reverse that chain, and the final route appears. So this is both a search strategy and a path reconstruction method. The pseudocode has 4 core structures. The open set is a priority queue ordered by FG score stores the best exact cost found so far for each cell. Came from stores the parent pointer for path reconstruction, and the heuristic function estimates remaining distance to the goal. Each loop pops the best open cell, checks whether it is the goal, then relaxes its neighbors. If a neighbor gets a better G score, we update G, recompute F, store the parent, and push it into the queue. The Python version is compact. We use heapq for the open set. Each entry stores F, G, and the cell. A G-score dictionary keeps the current best exact cost came from remembers the parent chain. In practice, the heap may contain tail entries because Python's heap does not support a true decrease key operation. So when we pop an entry whose G does not match the current best score, we skip it. The rest is just neighbor generation, score update, and path recovery. The algorithm is optimal only if the heuristic is safe. The first condition is admissible. That means h of n never overestimates the true remaining cost. The second condition is consistent. That means the estimate at one cell cannot break the edge cost structure when you move to a neighbor. Intuitively, the heuristic should decrease in a controlled way along edges. With these conditions, once the goal is selected, the best path is guaranteed. Without them, the search can become faster looking but incorrect. If the heuristic is 0 everywhere, then f of n becomes exactly g of n. In that case, E star becomes Dijkstra. So it is not replacing Dijkstra with a different idea. It is extending Dijkstra with extra guidance toward the goal. This is the cleanest way to connect the two algorithms. Dijkstra is the zero heuristic special case. Not every heuristic is equally useful. A weak heuristic stays safe, but it gives very little direction, so the search spreads widely. A good heuristic stays safe and sharply focused, so the search touches fewer cells. An overestimating heuristic may look fast, but it can skip the optimal route because it is no longer trustworthy. So heuristic quality controls efficiency, and heuristic safety controls correctness. This method appears anywhere we need a shortest path to a goal in a structured search space. In games, it moves characters through maps with obstacles. In robotics, it plans movement through discrete environments. In route planning, it uses a domain-specific estimate to reduce wasted search. And in puzzles or state space search, it guides exploration toward a target configuration. The common pattern is always the same: exact cost so far plus informed estimate to the goal. The mental model is short. Dijkstra says expand the cheapest known path so far. This algorithm says expand the path that looks cheapest when you combine exact cost so far with estimated cost to the goal. G is the history, H is the guidance, F is the priority. Parent pointers recover the route, and heuristic safety keeps the answer optimal. If those 5 ideas are clear, the algorithm is no longer just code. It is a system you can reason about. A good practice ladder is simple. First, run it by hand on a small grid. Second, implement G, H, and F without path reconstruction. Third, add came from and rebuild the final route. Fourth, compare 3 heuristics, 0, Manhattan, and an overestimating version. If you can explain what changes in each case, then you understand both the mechanics and the boundary conditions. Thank you for watching. I hope you enjoyed this walkthrough of E star with clear visuals and step-by-step reasoning. Stay tuned for more algorithm videos like this.